Welcome back. Good morning. Any questions before we start? Okay, so let's jump into our discussions from last time, which was about the conclusions of linear models, right? So we've been talking about linear models for a long time, right? You've been hearing W transpose X for many, many weeks. So I promise this is the last time you're going to talk about W transpose X, which is essentially a linear model, right? But one thing I wanted to sort of talk about before we move on is this very interesting discussion. Usually you won't see this in many classes, but I still want you to sort of get a sense of this, right? So there is some difference between regression and classification, right? In regression, we try to minimize, when we are trying to training, when we are doing the training, we try to minimize, or we want to find the weights that minimize our error. We want to be as close to the training data as possible, right? However, in classification, that's not the case. In classification, what we need is an ability for that line to split the data into two parts cleanly, right? That is the idea. So which means that an ideal loss function, when you write a loss function, should look something like this, right? So we want to find W and B, which are the parameters of our line or plane, such that on the training data, let's say you have n training examples, you want to minimize the number of times you make a mistake, right? That's the thing that you want to minimize. So this quantity over here, right? So this is the prediction that you get, and then when you multiply it with the true label, if that is less than 0, that means you've made a mistake, yeah? So this indicator function counts up all the mistakes, I mean this summation. So this is what we want to minimize, and of course then we put some regularizer next to it so that our solution is not overfitting too much, right? So but the problem is that this kind of function is not something that we have seen in any of the classifiers we have talked about so far, and the reason for that is that this function is not a smooth function, right? So let's assume that our data, that let's say we just have one training data point, right? I don't know what the date is. It's okay. So let's say we have only one training data point, which is X, and then we have corresponding ground truth or the label, which is Y, right? And what we want to minimize is, let's say our objective function is this 0, 1 loss, which is, so the objective function, and for now let's ignore the regularizer part. So objective function is going to be either 1 if W transpose X plus B, right? And let's assume Y is 1 plus 1. So Y is the positive example, and same logic would apply even if you had a negative example, but let's say it's positive. So this will be 1 if W transpose X plus B is less than 0, right? Because according to this classifier, you are predicting it to be a negative point, whereas it is a positive point, and it will be 0 if W transpose X plus B is greater than 0, right? So that is the function. So if you plot this function as a function of W transpose X plus B, right, then this function looks like this. So if it is greater than 0, then the loss is 0. So this is the loss. So the loss is 0 if it is greater than 0, and it is 1, this is 1 if it is less than 0, right? So this is how the loss function looks like. So the reason I drew this is because this immediately tells you that this loss function is not easy to differentiate. You cannot compute the derivative of this loss function because it is not smooth, right? So this is why different classifiers try to come up with some other loss functions which approximate this loss function, right? So if we talk about perceptrons, so in perceptrons, the loss function looks like this. It is 1 minus W transpose X plus B square, right? I'm assuming that Y is 1 here. This is actually Y. So this is the loss function for logistic regression, for perceptron, which means if I draw it, it will look like this. When this quantity is 0, the loss will be 1, right? So it will, and then it is a like a parabola, so it will look like this. So the loss function looks like this. We wanted this loss function, but we are working with this because this is easy to differentiate, right? But it's a little strange loss function, because if you think about it, it's sort of what it tries to do is it tries to find solutions which are as close to 1. And it actually does not like solutions in which W transpose X plus B is very large, even if it is on the right side, right? Even if your W transpose X plus B is greater than 0, which is good because now you can predict it correctly. But Perceptron just says that, I want it to be around here, and if you move either way, I'm going to penalize you, right? So this is, some people call this an issue with perceptrons, right? Another function is what we call logistic regression. Let's use this one. So of course, when we discuss logistic regression, we never looked at it as a loss function. We always looked at it as a maximizing the likelihood, right? But you can flip it around and you can write the loss function as well. And what you will see there is that it looks very much like a log curve. So I'm just trying to check my notes so that I don't make a confuse you later. But I mean, this is something that you can do at home, but the point is that this loss function, as it is in our notes, is called logistic loss, and it is proportional to log of 1 plus e power minus W transpose X, right? So that is how the logistic loss looks like. I think there's a half sign, that's why, or maybe you just write it as this, because everything else is a constant. So if I plot this, right, so when W transpose X is 0 here, this thing is going to be 1, but this is a log function, so this will look like this. Of course, never asymptotically it will go to 0, but this is how the log loss will look like, which means that it's doing slightly better than squared loss, because in squared loss you are penalizing it once it is greater than 0. Here you are penalizing it, but you're penalizing it less and less and less, right? So this is logistic loss. Now let's look at support vector machines, right? Use a pencil for that. So support vector machines, of course, we have looked at the formulation in a slightly different way, that we tried to maximize W, and then we tried to also put some constraints so that it's on the right side. But if you think about those slack parameters, right, those slack parameters are kind of the loss that we are trying to admit there. So the slack parameter is just if your if W transpose X is plus B, right, is greater than 1 for a positive example, then this loss is actually 0, right? We don't admit any loss, right? Else the loss is 1 minus W transpose X plus B. That's how far are you from the margin on the wrong side, right? So this loss is also known as the hinge loss. So we call this hinge loss because if I plot it here, it will look like this. It's going to be linear until this point, and after that it's going to be 0. So think of it as like a door hinge here. So it's a hinge loss over there. So these are the 3 different ways to model the loss, right? And that is the difference between these different linear models, is that the way they model the loss is different. And if you think about it, at least I would always feel that hinge loss kind of approximates the 0-1 loss better than squared loss or logistic loss, right? And that is why support vector machines also became quite popular, at least more than perceptrons, because they were modeling this loss in a much better way. All right, any questions so far? Okay, so let's move on. Now there was another topic about, so I mean the point is that let's say tomorrow you sit down and say, I want to come up with my own linear model. What you need to do is you need to come up with a new loss function, right? That's one thing. And the other thing that you want to do is to include a different regularizer. So you can either change the loss function right? Or you can change the regularizer. Now let's look at the regularizer. Now in regular, the role of the regularizer term is that you want it to be as sparse as possible, right? If you want to do something like a feature selection, you want most entries of this W to be 0. That's what kind of lasso does as well, right? So what we really want it to do is you want to have a loss function which basically counts the number of non-zero entities there are, right? So this could be a good loss regularizer, which is essentially counting the number of non-zeros in your W. So you penalize that here, right? So you want a solution in which this thing is as high as possible. But again, if you look at this function is again not smooth. It's a step function, right? It takes value 0, 1, 2, 3 all the way to D, which means that again optimizing this is hard. So what people have done is that they have approximated this with different types of regularizers. So we have seen some of these, and the reason they do that is because then it's relatively easier to optimize on, right? So we have seen the squared loss, we have seen which is in ridge regression, we have seen L1 loss, which is in lasso, and then you could have more as well. So in future, you can come up with a new linear model in which you have a different regularizer, all right? The only thing that you need to ensure is that you should have a way to learn that, right? You can't just say, I'm going to have cos of W transpose something as my regularizer. You can't stop there. You will have to also show that here there is a way to optimize for this regularizer, all right? So that is the point. So that kind of concludes our discussion on linear models. Any questions? Okay, so now let's move on to the next one. So we've been talking about linear models, but the next part is what really makes it even more interesting, which are kernel methods. And we are going to sort of look at some motivation for kernel methods. Then we are going to look at 3 different types of kernel methods. So kernel logistic regression, radial basis function kernels, and then support vector machines with kernels in that, right? The primary objective of kernel methods, there are twofold, right? So let's get started with that. All right. So far, when we have looked at linear models, right, we have assumed that our x is always a vector of some D features, right? We have started from, I don't know when, even when we are doing candidate elimination and to neural networks and so on, we have always assumed that x is a feature vector, right? And then we come up with these W's that you can multiply with x, or we come up with naive Bayes assumption where we say, you know, each value is independent, right? So that's good, but not all data in the world is represented like that, right? For example, what if the data that you're working with are genetic sequences, right? So the DNA or chromosomal sequences of different lengths. How do you put that into an X, which is a fixed vector, right? What if your objects are graphs or text or fruits or animals, right? You can't stretch it into a vector X. So that becomes a problem, right? We do want to apply these linear models to that kind of data, but that data is not in that form. Now, there are 2 ways to address that issue. One is that you can do some feature extraction on the data, and get some D features out of that. That's kind of what we did when we were looking at the tumor identification problem. You had these tumors, which were essentially these blobs inside images, and then somebody looked at them and then extracted these features, right? That's one standard way to do things. However, there's an issue there that a lot of times this feature extraction is not very natural. There is no good understanding as to what features are good, right? What should we extract? Have we extracted everything, or have we missed some of the key ones, or have we extracted too much of redundant features, and so on, right? So that's a problem. So how do we move from that? So what happens is that in many domains, even though you might not be able to represent your data, right, into a feature space, a D-dimensional feature space, R to the power D, it sometimes is more natural to be able to compare them, right? So in many domains, you might find very good ways to compare objects. So for example, when you talk about strings, right, 2 strings of ACGT, you can compare them using something like an edit distance, right? Or you can do length of the longest common subsequence. There are a lot of similarity methods for comparing graphs or trees, right? So sometimes that is easier. Instead of first converting into an x-dimensional vector, sometimes computing a similarity function is easier. We call these similarity functions as kernels. So these are like these primitives that we might have from the domain that allows us to compute similarity, all right? We cannot represent it in X, but we can compute similarity. So what can we do with that, right? So that is the idea. So the main point is that there's a similarity kernel, which is domain-defined measure of similarity, something that the experts have given us, saying this is how you compare an apple to an orange, or this is how you compare two strings or two graphs or two pieces of text. Okay. Now the question is, can we apply regression or logistic regression to in cases where data may not be represented at X as X, but we have a similarity kernel. All right. So this is sort of the core question of kernel methods: is can we apply all of these different methods which assume X is in d-dimensional space without having X in d-dimensional space? The only thing that they rely on is this availability of a kernel function, which given two objects can give you the similarity or the distance between them. All right. So that is the base question that we want to start. So the first thing we're going to look at is, can we use this for regression? All right. So let's look at that here. Now, if you remember regression, right? That was a long time back. But the ridge regression estimate. So let's talk about ridge regression. And regression would be same as ridge regression with lambda as 0. But the estimate for ridge regression was lambda, and you all did this in right, which means that when I get a new data point for a new object x star, so far we are still assuming that x star is in RD, right? Otherwise this whole thing doesn't work. Y star, the prediction is going to be W transpose x star, right? So if I replace x star here, it will look like this. Oh, sorry, W transpose here, transpose Y, transpose x star, right? Which means that I still need data to be a vector, right? If it's not, then you can't apply it. But what we can do is we can rearrange this term, all right? We can rearrange this term using something called Sherman-Morrison-Woodbury formula. So there's a matrix inversion lemma, which is fairly popular. If you look up the matrix cookbook that I talked about, it's on page 120. What that tells is, I mean, basically what it says is that if you have some expression like this, A plus some BCD inverse, you can rearrange it in a certain other way. The reason it helps in mathematics is that way you can, instead of doing matrix multiplications in one way, you can do it in slightly different way. So look up this Sherman-Morrison-Woodbury formula. You can find it in any math book, right? But what I'm going to do is I'm going to apply it here. So if I apply it here, this Y star will look like this. It will be YT. Well, actually YT will come from here, right? YT lambda IN this is the same as this, just by applying the Sherman-Morrison-Woodbury, man, that's a long name, but this formula, all right? Right, this matrix inversion lemma actually says this. I have it in the notes. It says that if you have an expression which looks like this, E minus F H inverse G inverse times F H inverse, this will be same as saying E inverse F H minus G E inverse F inverse, right? When you look at it, you say, oh yeah, obviously. But this is what we have applied in this case. All right. So we treat this quantity as E, one of the, we can treat H as in just an identity matrix. So what you see here is that earlier we were trying to take an inverse of this matrix, right? This matrix was D by D, right? This matrix will actually be n by n. So you are solving a slightly bigger problem if your n is greater than D. But the good thing about this is that now when you look at this formulation, things start looking very interesting, right? So you can rewrite this as y star is, well, not rewrite, but just want to bring your attention to this. So let's look at where x goes, right? X is here, both x and x star. So this was training data, this is our true new test object, and this is our x, right? These are the two places where x are. So what we are trying to do is, we are trying to figure out if we can somehow eliminate the need for having x, and if we can just replace it with just a kernel computation, all right? So let's look at x transpose. In fact, I don't want to write too much, so let's go here. So what is x transpose, right? So x is your input matrix where each row is one data point, and x transpose the transpose of that. So if I multiply x with x transpose, it will actually look like this. So where this quantity here is nothing but x1 transpose x1. Guess I have to write it. Right, this should be clear, but let's just go through it. So x transpose, right? So x is a sort of a matrix in which each entry here is x1 transpose because it is in a row, right? x2 transpose, x3 transpose, and so on. And then x transpose will be just a transpose of that, right? So it will be actually it will be a matrix in which you have x1, x2, x3, and so on, right? So I mean, each one of them is a row vector, and here each one of them is a column vector. x1, x2, x3, so on, right? So now if I do the matrix multiplication, what will happen is that each one of this quantity will get multiplied with each one of them, right? So this is x is n cross d, this is going to be d cross n. So what you will get is n cross n matrix in which any arbitrary entry, the ijth entry, is just xi transpose xj. All right, this is going to be x1 transpose x1, x2 transpose x2, and so on. So this is the part that you need to be clear on, but this is fairly easy to understand if you just sort of maybe take an example and work it out, right? And then the another place where x occurs is this x star, right? So let's look at that as well. So what is x star, right? So remember, x is a matrix in which each row is one of your training data points, and x star is just x star. So when you multiply this, this is n cross d, d cross 1. So it will give you a n cross 1 vector, right, in which each entry will just be x1 transpose x star, x2 transpose x star, and so on, right? So what I have done here is in this in this slide is that I've written that inner product as this, which is another way to write the inner product, right? So that is the point. So let's keep this information with us. Now let's say I want to apply instead of just working with x, I want to work with nonlinear versions of x, right? So I want to get nonlinear boundaries. So one way we saw in our previous discussion is we can do that by applying some basis function, right? So let's say I have a vector of basis functions. So I can apply this set of basis functions on each of my data point and get a new data matrix, right? So basically x1 will become many p values in which I have applied phi1, phi2, and phi p on x1 and then on x2 and so on. So this will be a new data matrix which will be n cross p, right? Because I started with n cross d, but I applied p basis functions on that. Now this is where you can also use the same philosophy for non-vector data. Let's say you have p ways to extract features out of this data. Let's say the data is a piece of text, right? and I have p different methods through which I can extract features out of it. So each one of this phi can be treated as a feature extractor, right? So essentially the idea is that eventually what you get is this new data matrix, which is your input data matrix, right? And now when you want to compute the prediction on a new x star, what you do is you basically solve this, right? It's very similar, except for x, instead of x, now I have this uppercase phi, and then you also apply the p basis functions on a new data point as well, right? So what you will see is that the same philosophy will work there as well, except that instead of computing the dot product between x and xi and xj, you will compute the dot product between phi of x and phi of the other one, right? So that is the idea. Now what kernel methods say is that we can now replace this product, right? So think about this product here. This product is basically computing the dot product between two vectors, right? So it's kind of computing a similarity, right? In geometry you must have read this notion of cosine similarity, right? So this is kind of like cosine similarity. It's not normalized, but it kind of computes. So if two points are very similar, then this value will be high, and if they are very different, then it will be low, and so on, right? So that's the idea of cosine similarity. So what kernel methods say is that instead of just computing dot products, let's replace it with any arbitrary similarity function, right? So what they do is they say, let's create a new data. So instead of this xx transpose that we compute, let's construct a matrix K in which each entry is not just the dot product between xi and xj, but it is any kernel function, and I'll talk about what suitable kernel functions are, but it's any kernel functions time between the two pairs. So here, just continuing our discussion over here, so instead of x extra, kernel methods, right? So remember, we wanted xx transpose, right, which is essentially this matrix over here, which is a series of dot products, is replaced with K, matrix K, and is n by n, of course, where K of I comma j is a some similarity function between xi and xj, right? So that is a point, because it turns out that actually to solve linear regression, you do not really need the data points, right? Even in the original form, if I had given you just this matrix, just the inner product between every data point, and also this vector, which is again inner product between every data point, you didn't really need your x's. You just needed a matrix in which you had computed the inner product between every pair of points. Now, if I replace that with this kernel computation, right, this x star is replaced with a vector, let's call it k star, where k star of I is just the similarity function, the kernel function between x I and x star, right? So now we can do the whole linear regression without really needing x's. All you need are these k's and this k star, right? Which means that now I can apply it even for data which is not a vector, as long as I have some similarity function, right? So that is the point behind kernel methods, is that you can work with data without really having the data. All you need is the pairwise kernel computations between every data point, right? Any questions so far? So this is a very interesting concept, and just rewritten it here, is that kernel regression now becomes this, right? So if you look at it, to compute the prediction for a new y star, you don't really need your x's at all. All you need is a k matrix. I mean, you don't need your x's to be a d-dimensional vector. All you need is a k matrix, which is computed using your x's, and another vector between the new data point and your training data examples. So now suddenly you can apply regression to classify strings into different categories, or actually predict something for them. You can also use the similar formulation for logistic regression if you can somehow show that all you need are these inner products. So the point behind kernel methods is that any machine learning algorithm in which the data points only occur as pairwise dot products, right, can be replaced by a kernel computation, and then you can generalize them to any kind of data. All right. Now the next question is, how do we construct a kernel, right? So what is a good kernel function? Can it be anything? So the quick answer to that is no, it cannot be any arbitrary functions, right? So it needs to follow certain properties. Of course, we have seen one kernel function, which is just the inner product, which will basically give you the same value, right? I mean, this is linear regression. But one thing you can do is you can come up with you can map your data into a higher dimensional space by applying basis functions, right? And then compute dot product there, right? So this is something that you did for your programming assignment 2, where you took your x's and you applied bunch of basis functions and worked with that. But the third approach is what we call a direct design, where we don't worry about x and we don't worry about the fees, right? Instead, we simply construct this K matrix. We also call it kernel matrix or the gram matrix, which just measures such that every entry in that gram matrix measures similarity between xi and xj, right? Now, somebody could argue that, hey, I can come up with any K function, but the point is that you can come up with any K function, but you need to guarantee that your gram matrix is positive semi-definite, right? So positive semi-definite in matrix terms is analogous to a non-negative number, right? So it needs to be positive semi-definite, and K should also be symmetric, right? Actually, I think it should be positive definite, because what will happen here is, see, I see. You need to take an inverse of K, right? So you need to ensure that this is possible, right? And this will only be possible if this quantity is positive definite, right? Positive definite is a non-zero number, right? So you can, if it becomes 0, then things will not be possible, right? It won't be possible to compute the inverse. So you want to ensure that whatever your K function is, the gram matrix that comes out of it is at least positive semi-definite, because after that, when you add this diagonal matrix, it will become positive definite, right? If lambda is greater than 0. So remember, positive definite and positive semi-definite concepts are something that I hope you know, but quickly, any matrix A is positive definite if Ax is greater than 0 for all x not equal to 0, right? For any vector, if you multiply A with x, then it should be greater than 0, and A is positive semi-definite if Ax is greater than equal to 0 for all x not equal to 0, right? And it's very easy to show that if A is positive semi-definite and you add a diagonal matrix with positive values on the diagonal, that will become positive definite. You can do that very easily with this formulation. But that is the requirement for any kernel function. All right, so now how do we come up with new kernel functions? Because I know all of you are excited about this, right? Say, hey, I can come up with any kernel function, go back and construct that and apply my linear regression to any kind of data, which is good. But of course, you need to make sure that these things hold. And one way to come up with kernel functions is to sort of start with some simpler kernel functions, which people have shown that these are valid kernels, and then build on that. So there are a lot of these rules that you can use to build new kernels. So for example, if you have an existing kernel function which is valid, right, which means that the K matrix will be positive definite, then if you multiply it with a constant value, that will also be a valid kernel function. You can add two kernel functions, still get a new kernel function. You can multiply them, you can take exponent, you can take a polynomial of that, you can multiply it with a vector. So you can do all kinds of things, and suddenly you have this whole suite of kernel functions that you could use. But the basic idea is the same, right? The basic idea is that you can replace your inner product that you see in linear regression with this kernel function computation. All right. So now let's look at some popular kernels. One of the very popular kernel is, of course, if K as I said, k is needed to be positive semi-definite. If k is positive definite, then that family of kernel is called Mercer kernels. And this is something, I mean, if you're interested, you can sort of read more about it. But for us, we'll sort of kind of stop here. In fact, we'll primarily look at this particular kernel function and then just stop there, right? All right, so here's the idea, right? So what this function says is that if given two data points, right, they could be, well, here we are assuming there are two vectors. Right? The kernel function says that the similarity between them is exp of this. All right, so it's kind of like a if you think about this value, let's say your x is just one dimensional. So this, you will see many names for this kernel. Sometimes we call it radial basis function kernel, RBF. Sometimes we call it Gaussian kernel because it has that Gaussian kind of term, or Gaussian. Sometimes we even call it squared exponent kernel, just because that's what it is, right? So k of xi comma xj is nothing but exp minus 1 over 2 sigma square. So this is like a hyperparameter of this kernel. And I'll tell you what that means. And you just compute the L2 square of the L2 norm of the two data points, right? So if xi and xj are in one dimension, right, they're just single values, then k is just exp minus 1 over 2 sigma square xi minus xj square, right? So what this kernel looks like geometrically is that, let's say this is your xi, right? So the value of this kernel will go like this. So for if xj is right on xi, then of course this will be 1, right? And then as you go farther away, the value of kxi xj will sort of go down like this. That's why we call it Gaussian, because it looks like a Gaussian bell curve, right? And how fast it goes down or how slow is determined by this sigma, right? So if sigma is very low, then this is going to go down very slowly. So it's going to be like this. It will go down, but slowly. And if sigma is very high, then it's going to be pretty sharp, like this. So sigma lets you do this. So essentially what you're doing here is you're defining a new similarity function, right? Where you're saying that the similarity of xj to this xi is going to be like this. If you're very close, then it's high. As you go far, it's lower, right? But because of this nice, smooth form of this function, we love it, right? Because that lets us do all of our differentiations and everything easily. Any questions? Yes, go ahead. Yes, so this function is only applicable when your x is vector.
So then why would you use it?
Why? Very good question. So the point is that, of course, we motivated kernels from the need when the data is not vector, right? But this particular kernel function only works when your data is vector. But the effect of this is, the reason we do that, so there are two reasons for using kernel functions. One was, of course, the need to bring in non-vector data, but other is to be able to map data into higher dimensions so that we can learn non-linear curves, all right? So if you remember in your programming assignment, what you did was that you used d polynomials to convert each x into d or p polynomial into p dimensional vector, right? So here what happens is, so essentially what you did was you had data in one dimensional space and you mapped it into 6-dimensional or whatever p dimensional space, hoping that data there will be easy to draw a line there, right? So that was the idea. And so when you bring it back, it looks like a curve, right? In fact, I'll show you a cool party trick over here. Let's say you have data like this. You have some positive points at the center of this space. Let's say data is in R2, right? And then you have negative points around this, right? Now, obviously, you cannot draw a line here, right? You cannot, even though this data is in R2, you cannot draw a line that separates these two types of points. But what you can do is something very interesting. So what you can do is you can map this data, you can transform this data into three-dimensional space, right? So suddenly, and I'll show you how to do it mathematically. Basically, if you take x1 square and x2 square and under root x1, x2, basically you have mapped data into three-dimensional space. And now what you see is, I don't know if you see, is that all of your positive points are here in the center, all the negative points are here, right? But now you can actually learn a straight plane that will differentiate these two types of points, right? So in the original space, there was no way you could have drawn a line that separates these 2 points. But in this 3D space, the data is the same. All you have done is you have mapped into high dimensional space. Now suddenly you can draw a straight plane, right? So that is sort of why we need these kind of methods, is so that we can project data into a space where you can draw linear hyperplanes, right? So not separable by linear plane, suddenly separable by linear plane, right? It's a cool party trick that you can use, and you will be the hit of the show. All right, but for here, so the point is that there are mathematical methods to do that. In fact, I have a small demonstration. Aha, here. Right. So if you look at the workbook on kernel methods, right? So there I have some interesting things happening. So of course this is a demonstration of the Gaussian kernel. So for different sigmas, right, this is what you get. So if your sigma is very high, then the similarity sort of is very sharp. Sigma is very low, then it's very smooth, right? But anyway, so let's say this is our data, right? So the data is on a line. That means data is one-dimensional, but the data looks like this, which means that there is no way I can draw a line that perfectly separates two types of data points. But now, if I change my data, if I replace x with x comma x square, so suddenly my data have two attributes now. I have mapped data into a two-dimensional space, right? And if I plot this data, the data looks like this in two-dimensional space, right? Which means that now I can draw this line, right? That's easy. And when I draw this line, it looks like this. Now if I take this line and put it back in the one-dimensional space, aha, it looks like this, right? And actually in one-dimensional space, you're only concerned with these 2 points. So basically what you have learned are two boundaries of this data set. But the idea is that you started with your data in lower dimension, but you were not able to draw a line. So you took it up and then you drew a line and you brought it back, it looks nonlinear. The same thing I can show in this 2D example. So for example, let's say our data is like this, right? So we have red points and blue points, no way to draw a line. But if I now apply my radial basis function, kernel, which means I plot data into a new space, and then I draw the lines and bring it back, they actually look like this, look like circles. Now I can do this, right? So that is a point. In fact, I don't know where my slides went for that. Aha, here, right? So this is what I showed you earlier, my party trick, right? Let's say if your data is like this, right? If I map this data into three-dimensional space using these basis functions, then you can draw a line plane in that, and when you bring that data back, it will actually look like a circle, right? So that is the whole idea behind these functions. But the reason I was talking about this this kernel, Gaussian kernel, is because what that kernel does is it actually maps your data into an infinite dimensional space, right? So that is the beauty of this, which means that you had data in some d-dimensional space. When you applied this Gaussian kernel, essentially the effect of this is that you have suddenly mapped your data. The fee that you would get by applying the corresponding basis functions will be in infinite dimension. And there you want to draw a line. So if you can draw a line anywhere, it's going to be in that infinite dimensional space. So that is why this kernel is so useful, is because it maps data into infinite dimensional space. But since we do not really need that representation, right? We never use the phi of x in kernel methods. In kernel methods, you never compute this, right? We just directly use k xi comma xj, which means that you do not really have to map the data into infinite dimensional space. But the effect of this is that data is getting mapped into that space. All right. And now why does it do that? There's a very simple proof for that. which is using Taylor series expansion. So we'll look at it in the next class. Today I want to cover a little more of that, right? But the main thing is that the effect of RBF kernel is like mapping data into infinite dimension space. You can come up with other kernels as well. So you can also come up with probabilistic kernels, where the similarity between two functions is given by the joint probability of them under some probabilistic model. So you can assume that xi and xj are being generated from some probabilistic distribution, right? And then you assume that they are independent. And what you can do is then just compute the product of the probabilities. That's also a valid kernel function. You can also come up with Bayesian kernel functions, where you say that I do not use a parameter, a point estimate for my theta, right? But I assume that I have some probability distribution over theta as well. And then the Bayesian kernel will basically compute these values for every value of theta, and then you're going to do that integral that we love, right? So this is the idea. Then you can also use kernels to map these methods for non-vector data. That's what we sort of started with. For example, you can come up with string kernels. So kernel functions that allow you to compare strings, like edit distance or inverse of edit distance. There are other kernels like pyramid kernels and so on that let you compare images or videos or anything, right? So that is the idea. So you can now suddenly compute kernel functions and then apply your methods. And what will happen is, because of those kernel functions, so every kernel function, what it is doing internally is it is trying to map the data into some dimensional space, all right, some finite dimensional or infinite dimensional space, and then you're applying your linear methods in that space, all right. But what happens is, because of the form of certain linear methods, like the linear regression that we saw, we do not really need that mapping. All we need, because eventually you would just be computing the inner product between points in that higher space, which means that you can directly apply that kernel function and you'll be done with it, right? So that is the beauty of all of this. All right, any questions so far? Oh, yes. So the question is, does this mean that linear regression will solve any problem if we apply suitable kernels to that? It could, but what I didn't tell you is that there is no principled way of figuring out which is the best kernel, right? So you might have some data and you might say that, okay, this is, let's say, data in 5-dimensional space, so you can obviously cannot see it, right? But then after that, it will primarily be just guesswork, right? You'll say, okay, let me apply this kernel, and it might work, it might not work, right? You could apply RBF kernel, which will basically map it to infinite dimensional space. But the problem there is going to be that, because the dimensionality is so large that it might happen that the method might fail, right? But you could do that. There is no question about this. There's a whole new, other area of regression methods, which are non-parametric regression methods, called Gaussian process regression, right? So there you basically work with kernel functions. And it works well, but then again, there are other issues as well, right? So for example, if you work with kernel functions, suddenly you have to solve inverse problems in which the k is n by n, right? Which means that if your data becomes very large, suddenly you have to solve this very large system of equations, which is n-dimensional. Whereas in original linear regression, this was d by d, right? It was x transpose x. So it could solve everything, but it's just that we don't know how to reach there, right? That's a good point. Any other questions? Okay, I guess we can stop here if there are no more questions, and then we'll continue this on Monday. But I think you have enough information to do your second gradients problem. So if not, just let me know. All right. Thank you. See you on Monday.